Hi everyone. This video is about a new searching technique called as binary search. If you have seen the last video where I have introduced the technique of linear search, and in the linear search, we saw how to search all the list items, which can lead to long run times due to um, having to get matched with all the elements as per our key element inside the list. So let's say, for example, searching for a contact on a smartphone one by one from first to last can be most time consuming task. So because a contact list is shorted, a fastest search known as binary search checks the middle contact first. Okay. And if the desired contact comes alphabetically before the middle contact, then in that case, binary search will then search the first tab, otherwise the last tab. And here each step reduces the contacts that need to be searched by the half. To okay, so 1 second. So here what happens exactly in binary search, that it's a bit faster in comparison to linear search algorithm for searching a list if the list elements are sorted directly and accessible, such as an array. So binary search first checks the middle element of the list, and if the list search key is found, I'm going to take you to one example here. Okay, the current example that you are viewing here. So let's say the search key is 16. So if the search keys, which is supposed to be looked through all the elements in the list, if the search key is found, then the algorithm returns the matching location. And if the search key is not found, the algorithm repeats the search on the remaining left sublist. And if the search key was less than the middle element or the remaining right sublist, then if I mean that's the case where the search key may be greater than the middle element. So it's a bit, it's not complex though. While I just talk you through it, it's a little bit complex to understand. So let's see this example here in this activity. Okay, so let me start the activity. Yeah, 1 second. So here the search key that we are looking for is 16 inside our list. Here through all these big boxes with the no color, gray color, and the light blue color with the unsearched, searched, and current. This is to point in what state our current list element is in. And this is the numbers list where we have multiple elements. And the first location with 0 is to be set with low. And the last location with the element 63 at the index 7 will be high. So in total, we have 8 elements inside the list. Let me go to the next step. Here, first, the middle element is to be determined. So what is the way here? Let me again show it to you. Okay, so first, after keeping track of the low and the high, the middle element is to be determined by this formula, the high plus low divided by 2. So 7 plus 0 divided by 2, which is your 3.5. So rather than taking the fractional value, because the fractional value doesn't have any meaning inside the list, we don't have any index numbered as fractional value. So you have to consider the whole value instead. So here the 3 is the whole value. So the mid value is now at the position 3, that is the element 14. So what happens here, the search key that you have, that is 16, it is supposed to be compared with 14, whether they are equal or not. If it's not equal, the next thing, what are you supposed to do based on the binary search technique? It has to determine the search key 16, which is to be compared with 14, and as they are not equal, so is it smaller or is it greater than the value inside the numbers list? So as you see, the 16 is greater than 14. So if the value that you are searching for is less than the value with which it has been matched inside the list, so there the next track is to go through the left half of the list. Okay, based on the mid value. If the 16 were here, in this case 16 is greater than 14, it has to see the right half portion of the list in which we have to search for the elements. Let's see that process. So now 16 greater than 14. So here low is to be determined as 4, high is 7. So now the mid is 5, and now 16 is to be matched with 24, which is not equal, and 16 is less than 24. So rather than seeing the right hand half, we will now consider the left hand half. So now the low as well as the high value is your 16, the element at position 4. So there is a match, and we found our search key at location or index 4. So this is the basic binary search technique. Let's implement this step by step in the form of an algorithm using the Java language. So I'm going to take you to the Java code here, where I already have the portion of the code already developed. It's kind of similar to the linear search technique. If you have watched the video of my linear search technique before this video, then you must understand I have the same structure here, the same package name, and I want to have some system in and out operation. That's why I have imported the scanner package, and then scanner statement. This is the numbers list, I, key, and key index variables. Uh, the next, through this for loop, I'm trying to print out the list what I have. Let me first execute. Okay, sorry, it won't execute here because I have not implemented the binary search. So first it should display the list, then which key I want to search for, that will be inputted here. Let me do one thing. Let me just comment them out so that you will see what am I trying to do here. Okay, so here is the list that we have. Let's say we want to search for um, 10 here. So now we want the index of 10 to be returned here. As we have not created a function for that in order to find out the key index, so that's why it's not displaying that. Let me just uncomment this again, that we should be able to execute it successfully. Now the next thing is that here the binary search function, which is yet to be developed or built, it's taking the array numbers as an input, this one, and then the key value, any key value that will enter. The last time as that you saw, that is our 10 value that I entered for the key for which I'm looking at inside the list. So let me create a method for that. I'm going to take it to this after the class here. Okay, well, so let's typing in our code. So this is the list and the key that I'm looking for, numbers and key, and using these arguments I'm going to create my code. So first thing first, here, as I want to find out the mid value always in the list. So for that, mid is the variable. I want one low value as well as one high value of integer type. Now I will use all of them. Let me do one thing. Let's initialize to 0, and high should be equal to the least that I have, numbers here. This is my least, should be equal to numbers dot length minus 1. So here these are the arguments initializations I have made. I'm going to use all this inside a loop. So what it will check, while it has to already always take the high value that we have, whether it's greater than or equals to low or not. If it's not true, then we have to come out and we just have to leave the loop. It has to be correct in order to keep on going with the process that we want to do here. So the mid value, let me put a space here. First thing first, we usually determine the mid value. So how to determine it? If you remember, high plus your low that you have, and then it should be divided by 2, and the whole number will be considered. So because of that, I have not included the remainder division, rather I have used the simple division to find out the quotient in the format of non-fractional value. Now next it will check if, sorry about that, if the numbers um, arrays mid position that I just found out from this statement here. So if it's less than the key that I'm looking for, so for this case I have to consider searching in the left hand side of the array or left half of the array. So mid less than key. So here at what I will do, first I need to find out what is the low value, so that should be mid plus okay, mid plus 1. Then you need okay, so now I am going to add another one condition, else if the numbers of arrays mid, let's say it's greater than the key value what I'm looking for, then the high value should be determined as the mid plus, sorry, mid minus 1. This is how the low and high will be determined. Now in the else part, main logic behind this is the determination of the low and the high value, because you need to find out the mid value each time. Up to the time if you have not found out the key value, so the mid value will be returned else. I think yeah, so if at the beginning that I have added while high greater than low, so if it's not true then it will just check on for the -1, return -1 if it's the element is not found. Okay. So with the binary search technique through our process here, um, okay, so if high value is the length -1, that is the last position, and the low value is the first position, first index. So if high is greater than equals to low, so first mid is determined by this formula. Then if the mid value is less than the key, now the here the low value will be the mid element +1. Okay, so the low value is determined, or else if the mid value that we found out in the list or in the array, than the key value, then the high value will be the mid -1, else will just return the mid as per our need. So using all these conditions, it will come here, return the key index, and if the key index is -1, let's say it's not found, then key was not found. Else, so we found the key at the index, that is our key index we just found out through the algorithm, through the function. So let me run the code. Let's say we want 10, it has to return 3. Yeah, so it's working and returning the index as 3. So here this is our basic binary search technique that you just saw right now. The thing is that first understand what are the process of achieving the searching technique. Based on the technique or the process in which you are solving this problem, you just write it down using the logic and just pick a language to uh, implement the logic in there. The next thing I'm going to show you the time complexity. How much time does it usually take for the two searching techniques that we have learned so far? So what is algorithm's runtime? It is actually the time the algorithm or the program takes to execute. So how many steps are there in the algorithm and how much time it can take approximately. It doesn't has to be exact, but approximate value is enough. So let's see the linear search first. If you remember the linear search, where each item has to be checked until it gets a match inside the list as per the key element. So there has to be one comparison. So each comparison it takes okay. So here each comparison it takes 1 microsecond. So if a linear search algorithm runtime is up to 1 second to search a list um, with 12 million elements. Okay. So like this, how much time it will take for different sized elements group. Okay. So let's say if you have 10 million set of elements inside a list. So based on this 1 second for 1 million element, it should be 10 second for 10 million elements, and like this it will go on. So let's say we have one Amazon online store. Okay. So the Amazon online store, it has so many number of element. Maybe it will have um, 200 million items. So it may require more than 3 minutes. Okay. For the comparison. So if an algorithm, if this algorithm typically uses a number of steps proportional to the size of the input, if you have n number of elements, there has to be n number of searches also. So if you have 32 elements in a linear list, it may require 32 set of comparisons at most. So how is it? Let's say one comparison if the search key is found at index 0, and you want two comparisons if you found the element at the index 1, because you have to search for 0 and 1 index and so on. So 32 comparisons in the search key has to be done if you couldn't find the element inside the list at all. So for at least n number of elements, where n can be any number. Okay, it has n number of elements, so linear search requires n number of comparisons, and the algorithm is set to acquire or require on the order of n comparison. So based on how many number of elements and how much time does it take, how many comparisons, based on that we have to determine the algorithm's runtime as the order of n. So it has to be order of n for linear search. So let's see what we have in binary search based on the binary search technique. So in the binary search technique, so binary search actually it's incredible efficient, kind of efficient in comparison to linear search, because you doesn't have to search for all the elements in the list. So during, let's say it will be more efficient in the condition where you are supposed to find an element within a sorted list. Let's say your list is sorted already, so in that way it will be more efficient. So during each iteration or step of the algorithm, binary search reduces the search space. So that is the time remaining the elements to search within by half. So the search terminates when the element is found, and or the search space is empty, element not found. So for a 32 element in the list, let's say you are not finding the search key that you are looking for, then the first it has to be halved by 16 element, because you are finding the mid element. Then it should be next half will be 8, next half 4, next half 2, and last 1, and then finally none. There are actually 6 steps for 32 element list, whereas in linear search it usually has to do 32 steps for searching the elements if you are not finding the element inside the list at all. So based on this analysis for an n element list, according to binary search, the maximum number of steps required to reduce the search space in an empty sublist will be log base 2 of n plus 1. How is it? Like you saw the example for 32 elements, how many number of steps required? 6 steps. So let's say this formula is working for that or not. So log base 2 of 32 is 5 plus 1, which is 6. That is equals to our number of steps required for this step. So this is how the time complexity or time consumed for the binary search technique is derived. So linear search is order of n, whereas binary search is log n plus 1. You can sometimes we also discard or avoid this plus 1, so it's kind of already always considered as log of n for the binary search technique. Hope you enjoyed this video and got some idea about the search technique, that is our binary search.